The beam comes from behind there.
Radiance beamline.
A beamline, yeah. It's so basically it's just a big vacuum tube that brings the radiation from the synchrotron source and then adapts that radiation to the type of experiment that you want to do. In this case, the experiment is a diffraction experiment with crystals from macromolecular samples, so of biological origin. So we're talking about proteins, we're talking about nucleic acids, complexes between proteins and nucleic acids, and things like that. The samples are very, very small because the biological materials are quite difficult to purify, to crystallize, to handle, and you know, they're very delicate samples. And so we bring the beam down to a focal point around here, from which we can, using this device which is called a goniometer, we can move the angle of the crystal with respect to the beam, either by rotating around this axis here, or by turning it around an axis around here, or by turning it around this big axis. So we can examine these three-dimensional crystal objects from all the different orientations, and at the same time produce diffraction images which will have black and white spots on, basically. If we examine this symmetrical object from every possible angle, for each angle we record basically the projection on the X-ray detector of the electron density, or the electrons that follow the path of the X-rays on the way out. So we get a projection of what actually scattered the X-rays in whichever direction, and you can then mathematically reconstitute what the molecule that did the scattering was. So that's basic technique of X-ray diffraction, and here it's specifically applied to macromolecular crystals. Okay. The interest of doing that at a synchrotron, I mean, almost all nowadays, I would say about 80% of all structures, three-dimensional structures of biological macromolecules are done with synchrotron radiation, with X-ray diffraction. And so almost all the detailed three-dimensional knowledge of these rather complicated molecules comes from X-ray diffraction. Now, of course, X-ray diffraction gives you a static picture, a one-off picture of how the protein looks in the crystalline form. That then has to be linked with other biochemical knowledge, or perhaps other measurement techniques, because you might want to look at, for example, the way complexes form, or the dynamics of complexes, or you may want to, but the X-ray diffraction gives you a very detailed picture. And apart from X-ray diffraction or nuclear magnetic resonances, those are the only two real techniques that can do that.
But did you use a continuous beam, or maybe how many collisions do you
Oh no, it's continuous. It's
continuous.
Well, could you be careful not to push the button? Otherwise it'll all go dark. Yeah, some experiments use the time structure of the beam. We use it as if it's a continuous beam. For us, the pulses are so frequent that it's continuous. Sorry, you had a question?
No, it's, you can only look at the structure that are crystals.
Yeah, there are other techniques for using solutions, but this technique uses crystals. And of course,
other beams? Or?
Yeah, well, other beams, the same beam on a different beam line. If you want to measure things in solution, you have to look at the scattering at much lower angle, and
do that with the synchrotron.
You can still do that with the synchrotron. The analysis of the data is quite different, and